And there's no way but also things that are now but at least
Okay, let's start notes for this is our final unit, area and volume. A lot of this will feel familiar. It's just that we're mainly dealing with definite integrals, but you know how sometimes definite integrals we may end up with a negative value, and we always said, oh, it's area related, but it's not quite area because we may get like a negative displacement. So to adjust for that, we're going to have a formula in place that will always give us a positive number, which we can now call area. But it's just really definite integrals. A lot of it will feel familiar. So we'll do that today. That shouldn't take the full period. We'll have some time to continue doing test review. So tomorrow's your test. And then Friday, we'll look at area problems from AP exam standpoint and just see how they ask questions about area. Next week, we'll have 2 days just to do notes. So we'll do this method, and then we'll do washer method and cross section. So we only have really 4 lessons within this unit here. And then we'll spend the week after next reviewing. And then after the 14th, we're just going to begin our AP exam review. So we're almost near the end, at least for this course. We have almost 2 full months for AP review. And we need it because there's just a lot to put together. You know, all the first semester content, putting it all together. So it's good that we have this much time to do AP review. Now, even during AP review, we're still going to have quizzes and tests, but so we're still going to have grades that will go toward your semester grade. Okay. All right, let's look at page 1. Okay. Sorry. So this is where we start off with vertical orientation. This is where we can imagine stacking vertical rectangles from one end of the boundary to the other end. Here's the formula. The formula, if we want to find area, this will ensure that we're always getting a positive number, is we're going to have a left bound and right bound. This is going to be where our graph or where our region will begin and end. And then the top graph versus bottom graph. The top graph is visually the one that is higher up on the y-axis, and the bottom graph is the one that is lower on the y-axis. Okay, so which is top graph minus bottom graph. And if we do that setup, then we're going to get an area of a shaded region, enclosed region, using our calculus integral notation. Now, everything has to be in terms of x. So our expression is in terms of x. Our bound is in terms of x. And one way that we can tell is you look at the left side. If your left side is y equals, that means whatever expression you're plugging in is in the proper form. So it could be y is equal to x squared plus 3. It could be y is equal to 4. We'll be using everything on the right side to plug into our expression, but then the left side is kind of giving us, okay, that this is in the proper form. If it's y equals, then everything on the right side is ready for either the top or the bottom graph. So example one, my top graph, the one that is higher up on the y-axis is the f of x. The bottom graph is the g of x. And then my bound is from A to B. So our area of this shaded region is the definite integral from A to B, f of x minus g of x, and then dx. So make sure you include your notations. We have integral and dx kind of acting as the bookends of your, to represent area. Okay, example two. If we want to find the area of the shaded region, my top graph is the f of x. And my bottom graph, what's the equation of this line? The x-axis, right? What's the equation of the x-axis? What's the equation of this line? Y equals 0, right? Y equals 0. So you have top graph being f of x, you have the bottom graph being 0, and then you're going from A to B. So our area of that shaded region is definite integral from A to B, f of x minus 0 dx. Now, the 0 is going to drop out, and you're just left with the integral from A to B of f of x dx. We've always been doing minus 0. Okay? We've always been comparing with the x-axis, but we've always dropped it out because it's just always, it's always 0, so 0 doesn't have to be there. But now that we're actually seeing, oh, there's a top graph and bottom graph with this formula, anytime you see an integral of f of x, it's always subtracting with, it's always in relation to the x-axis. That's why there's that minus 0, but it ends up going away because that minus 0 can be dropped. So I want to do another example. I'm going to call this example 2b. Now, what if I have a graph that looked like this? Let me call this g of x. And I want to find the area between A and B, or let me call this between 1 and 2 of this shaded region. We're also going to, again, this is the x and y axis here. Now, we want to create a formula that will get us an area of this region and no longer a negative value. So we'll say the definite integral from 1 to 2. All right. What is the top graph? What is higher up on the y-axis of the shaded region? It's this, right? What is this boundary? What is this? Y equals 0. So it's going to be 0 minus what? G of x. So top is the 0, bottom is the g of x. Whatever is higher on the y-axis is the top. Whatever is lower on the y-axis is your bottom. So we can drop the 0 and just keep the negative. So 1 to 2, negative g of x dx. Now, normally, if we just did the integral of g of x, we would be returning a negative number because it's all below the x-axis. And this negative is doing the job of countering that negative. And this will end up giving us a positive value now because we're going through this proper top minus bottom formula. All right, example 3. Find the area of the region bounded by y equals x squared. Y equals x squared is the parabola here. And y equals 2x plus 3, that's the linear graph here. And we want to find the area bounded by it, so basically the region in between. So let me shade that in. We're going to find the area of this shaded region. So here are the steps. We're going to find the bounds. So to find the bounds, we're going to find the intersection of the two graphs. The intersection of the two graphs will act as the boundaries for our integral. So to find the intersections, we're going to set the equations equal to each other and solve for x. So we'll set these equal to each other, solve for x, and we should be able to find these two endpoints algebraically. So set equations equal. Anytime we have a quadratic, we have to get a 0 to show up. So let's move everything over to the left side so we can go through our factoring steps. All right, multiplies to be -3, adds it to be -2. So -3 and 1. Solve for x, we get 3 and -1. So that tells us we have one boundary being -1 and the other one being at 3. So those are our upper and lower bounds that we're going to be starting and ending in our problem. Okay, so let's set up our area formula. Area is definite integral from -1 to 3. Top minus bottom. The top is the graph that is higher up. Let me, I like to do this sometimes. I like to do a representative rectangle. Technically, we're adding infinitely thin rectangles from one end to the other. Having a representative rectangle just helps me to identify, okay, whatever the top of my rectangle is touching is the top is representing the top graph. Whatever the bottom of my rectangle is touching, it must be talking about the bottom graph. So the top is my linear, right? So the one that is higher up is that 2x plus 3. So we'll do 2x plus 3. That's my top graph. Minus the graph below is the curve. That's the x squared. I think it's a good habit to put parentheses around the bottom function. It's not going to matter right now because there's only one term. But if there were multiple terms, we do need to protect that with a set of parentheses because we're trying to subtract everything that comes after it. So I'm always going to put a parentheses there as a reminder that the bottom function is followed by a negative sign. And we got to make sure that we're careful with what happens after a negative. Okay, eventually we're going to transition and just make the calculator do this for us, but for now we'll do this by hand. All these terms are just power ruled problems, so we'll go through power rule first, and then we can plug in our upper and lower bound. So we go through power rule. Okay, no plus c, right? Because we have bounds, so half bracket from -1 to 3. Upper bound first, minus lower bound. You can cancel the 2's out. Upper bound is 3 cubed plus 3 times 3 minus 3 cubed over 3 minus big parentheses. Now we'll plug in the lower bound in this set of parentheses. Lower bound in for all the x's, -1 squared minus 3 plus 1/3. All right, all these numbers just combine to be 32 over 3. So 32 over 3 is the area of that shaded region. So I think everything here feels pretty familiar. Top minus bottom, from left to right, everything feels like something that we've seen before. On the next page, the harder one to wrap our head around is going to be, what if we have two graphs that are not functions? but they're to the left and to the right of each other. We can still find the area, but now everything's in terms of y, and it just feels a little bit off because the orientation is not what we're used to. We're not used to working in terms of y. We're much more comfortable working in terms of x. Okay, page 2. Right. So now let's say we have two graphs. Now these are not functions because neither of these graphs pass the vertical line test. But let's say, but these are equations. It's in terms of y. So x equals f of y and x equals g of y. And if we have two graphs that are to the left and to the right of each other, they're not going to be functions, but they're going to look a little strange because they're going to be x equals y squared or x equals y cubed minus 3. But we can still follow the same process. We can still find the area, right graph minus left graph, but everything will be in terms of y. And our bounds is going to be from y1 to y2. So remember how if we have a top minus bottom, we're stacking vertical rectangles from the left boundary to the right boundary. So we're kind of stacking them this way, right? Now, if I have a right minus left, then I'm also doing rectangles, but my rectangles are going to be stacked horizontally. So I'm going to stack the horizontal rectangles from the lowest y value to the highest y value. So everything is just kind of opposite with the way that we're thinking here. But we can still find the area. We're just stacking our rectangles differently than our normal vertical rectangles from left to right. So the graph on the right is the one that's further to the right on the x-axis. This is the one on the right. And then the graph on the left so my area, we're just going to follow the formula here from y sub 1 to y sub 2. So the lowest to the highest y value. So lowest is c, highest is d. So the integral from c to d. And then right minus left. Right is the f of y. Left is my, it's hard to see here. I meant for this to see, say g, x equals g of y. So it's f of y minus g of y dy. Everything is in terms of y. Okay, let's try an example showing that right minus left relationship. Again, it's going to feel a little weird because we're not used to equations that are not functions, or we're more comfortable working with functions. So the equation on the right, this is the x equals y plus 1. That's going to be the linear graph. And then the curve is going to be x equals 1/2 y squared minus 3. Notice that the left side is showing x equals. So anytime you see x equals, you know that it's a good candidate for right minus left because everything on the right will be in terms of y. So I like to use that left side x equals to help me recognize, oh, this is going to be a candidate for right minus left and not for a top minus bottom. But we're going to start the same way. We're going to find the intersections between the two graphs. But now we're not going to solve for x, we're going to solve for y. We want to find no longer the left and right x values of our boundaries. We're trying to find the lowest and highest y values of our boundaries because we're stacking our rectangles. We're stacking, we're accumulating the area differently, horizontally from lowest to the highest y value. So here are my equations. I have 1/2 y squared minus 3 equals to y plus 1. So I want to find out where are these two graphs going to intersect, and wherever they intersect, they're going to return me the y values of these intersections. Now, I do want to factor this, but I don't want to factor with a 1/2 in the way. So to make it easier on myself here, I'm going to just multiply everything through by 2. So I don't have to deal with factoring with fractions. So if I distribute a 2 through, I should be able to get all of my coefficients be nice integers. So multiply 2 through with every term. 2 times 1/2 is just 1. 2 times 3 is 6. 2 times y is 2y, and then plus 2. All right, so we want to factor. So let's bring everything over to the left side. Go through our factoring steps. Multiplies to be -8, adds up to be -2, y minus 4, y plus 2. Take depth integral from -2 to 4, lowest to highest y value. We want to follow the formula here, right graph minus left. So the one on the right is the one that's further along the right, further on the x-axis. So further right is the x equals y plus 1. You can also draw a representative horizontal rectangle. We're stacking infinitely thin rectangles that are in this orientation. The right endpoint of my rectangle is hitting that y plus 1. So that's my graph on the right, minus the graph on the left. So the left is the curve. So big parentheses. This one, we do need parentheses because we have multiple terms. So 1/2 y squared minus 3 dy. All right, so again, it's just power rule, but everything's just in terms of y. I'm just going to arrange them a little differently here. So we do power rule, power rule, power rule, and then we plug in our upper and lower bound. Okay, we won't have to worry about doing a bunch of messy calculations here. Eventually, our calculator will do all the work for us, but just want to go through the steps here. Ends up giving us 18, and so 18 is the area of the shaded region. Last example, and then we can go and do some more test review. Represent the area in the shaded region to the right using integral notation. So notice that these are two shaded regions here. Is the graph going to be on top the same in the left and the right region? Right, there's a change, right? There's a flip-flop. The curve is on top for the left region, but then the curve swaps to the bottom. So we need two separate integrals to ensure that we're getting positive number here and a positive number here. So we'll say depth integral from 1 to 2. From 1 to 2, my top graph is the curve, my bottom is the linear. So it's going to be f of x minus g of x dx. So that will take care of the left region. And then the region on the right, the larger region, is from 2 to 4. And there's a change in top, right? So the top is now swapped over to the linear, which is the g. So it's the g minus the f dx. Okay, so if we were to somehow find these two functions and represent them in the integral, this will ensure us that we get a positive number here, positive number here. Otherwise, if we just did f of x minus g of x, then we're getting displacement. Then these values may cancel out, and we're not getting the true area. All right, let's go to, let me see if I can pick out some problems for us to try. This is page 10 off of your homework packets. I want to do a population y equals c e to the kt problem. So page 10 off your homework packet. I don't think we've done this yet. So the population problem or the CE to the KT problems that we've been doing have been where you plug in solve for C first, then solve for K, and then find the whatever missing information they're asking for. But sometimes the problem may not be in that order. Sometimes the unknown could be the C value. So okay. So radioactive decay. Radioactive radium has a half-life approximately 1,599 years. What percent of the given amount remains after 100 years? So we're always going to start off with our order pair here, gather some information, time and radium. Time is always your x, and whatever the other variable is going to be, is always going to be your y. So the earliest time is present day because everything is in the future. So we know that currently we have a starting amount, a given amount. So the unknown starting amount is C. We know the half-life is 1,599 years. So we know that in 1,599 years, what's going to happen to this unknown amount? What does half-life mean? This is going to decrease down to what? Yeah, 1/2, right? Whatever my starting amount is, it's going to decrease by half. So 1/2 C or C over 2. I'm going to do 1/2 C, but C over 2 is fine. It says what percent of the given amount. Let's just look for the given amount. Let's just look for the given amount after 100 years. So whenever you have this setup, you're not going to start with 0C. If you plug in 0C, you're not going to get any progress. So you're going to start with this 1599 1/2 C. So 1599, we can plug in for what? What variable? P, and then the 1/2 C, we can plug in for the R, all right? So I have my equation, R equals C e to the KT. So R gets replaced with 1/2 C. K gets replaced, sorry, T gets replaced with 1599. What's nice about the setup? What can we do? What can we get rid of? C's, right? If I divide both sides by C, that can allow us to focus on, I mean, eventually we do want to solve for C, but we can at least focus on solving for K, which can act as a stepping stone to eventually solving for C. So we have 1/2 or 0.5 equals to e to the 1599K. I want to solve for K, but K is stuck in the exponent. So what can we do to allow that K to come down? Introduce dash log. I'm going to change that 1/2 to be 0.5, so I don't have to deal with a fraction. Now that we're inside a natural log expression, what can we do with this exponent? Bring it down in front, yeah. What do you know about natural log of E? Just 1, so that's nice, that goes away. Divide both sides by K, sorry, divide both sides by 1599, and then we have K by itself. Let me change this problem a little bit to make it more familiar with, or more similar to what we're going to see on the test. Let's say after 100 years, there's 50 grams remaining. Okay, 50 grams remaining, and we're trying to solve for C. So after you found K, now we can update our equation, and then plug in our initial data, further data to help solve for C. So let me update my equation. R is equal to C e to the KT. Again, you want to hold on to your K value as exact. If you convert that to a decimal, it's going to decrease the accuracy of your final answer. So this is my updated equation with my K value. So now I can plug in 100 in for T, 50 in for R, and that should allow me to solve for C because that will be the only variable remaining. If I solve for C, then I have my initial amount. And now it's just a bunch of calculator entry here. E to the natural log of 0.5 or 1599 times 100, that's going to be just some decimal value. Divide that over to the left side, and then you have C found. Okay, let's practice entering that in. C. Are we, see if we agree. So we're not going to decrease much in 100 years because it's going to take almost 1,600 years for that amount to decrease by half. So even after 100 years, it's only going to go down by 2 or so grams. Is that what you guys got? Yeah, solving differential equation. We've done some of that. We've done quite a few of that. Canton equations, linear approximation, creating a slope field, multiple choice slope field, y equals c to the kt. We just did that. Completing the square. Oh, I do want to talk about this. Let's talk about formulas here. It's formulas that you want to be able to work on. So this is if you can go to page 19 in your test review packet. So you're responsible for the formulas from page 19 to page 20. But you can cross off 9 through 16. Okay, you don't have to worry about those for the test. But I do want you to know the original 6 trig rules. I do want you to know natural log of u and e to the u's derivative. And then page 20, we need to know all the integral rules. Everybody good? Okay. And then page 21 and 22 have all the formulas. So I think it's good tonight if you can practice all your rules and then check to see how well you're able to recall those rules. And then worksheet 4 is a good mock test for you this afternoon or this evening when you're preparing for your test. And this is also going to be the worksheet. Worksheet 4 will also be what I'm going to go through tomorrow. I did a little bit of it this morning in the morning review, and I'll continue reworking some of those problems as well as finishing those problems. Look over your quiz. All those problems from your quiz we need to be able to do. We did a synthetic division one yesterday. I complete the square if you see that it's going to be a trinomial in the denominator and there's a gap in degrees. Let me see if I can do one arc trig problem with you before the end of class. Okay. So just find any empty space that you can. Let's see. Right. How do you know this arc trig problem? And not a U substitution, not a normal U substitution problem. Yeah, difference in degrees. Degree 2 versus degree 0. That's a large enough gap for us to have to explore arc trig. Trinomial, so you know you got to complete the square. The formula that fills in that space is b over 2 squared. My b is 4, 4 over 2 is 2, 2 squared is 4. The whole point is this should turn into something that is usable for our u value, but we can factor that, multiplies b4, adds up to b4, 2 and 2. And 17 minus 4 is 13. Get both of them into a set of parentheses. This is easy. This is should just be duplicate. And 13 can be rewritten as what? For 13. So now let's reset, right? We have our a and u value in front of us. Your a is the constant, your u is the variable. Should match up nicely with arctangent, right? Arctangent is the only one without the square root. There's no leftover coefficients. So we're just following the rule. The rule says 1 over a arctangent of u over a plus c. So my a is root 13, but I still need to hold on to this 3, right? This 3 is going to have to come out as a coefficient. So that 3 is on top or in front of my 1 over a. So 3 times 1 over a arctangent of u over a plus c. All right, so tonight's study for your test and morning help session tomorrow, 7:15. I'll send out a reminder this afternoon. Come get the funds.